All right, I'd like to do a few more examples of uniform circular motion in which different kinds of forces can play the role of the centripetal force. Remember, that's the center-seeking force that allows for an object to travel in a circular path at constant speed. And our basic working equation for that we'll be using all the time is our centripetal force is equal to mv squared over r. And so in the next example, let's say we have a car on a flat racetrack. Say that the radius of the racetrack is 200 meters. And I'm not even going to tell you what the mass of the car is, but it turns out that's going to cancel out. Because what I'm looking for here is to find the maximum speed that this car can travel in this circular path before the car starts to slide. Okay, and so first we have to identify then, and here I've got two different views of this, which we could also see by looking up at the data projector for a second, slightly better pictures. Here's a car, and it's going around a circular track, and so we see then that the force that is providing the circular motion, the centripetal force, is the static friction force. Okay, and so you go, well, static, what are you talking about? The car's moving, but it's not sliding. Okay, and so it's static friction that is allowing this car to stay on the road. And so if we come back down here, we can see that this car's natural path in the circular, so it's going around in a circle like this, coming back out and then back in, as you can see from this picture, which is the top view. This is the velocity that we want to maximize. So that would be, from this view, the car would be moving into the board, but around in the circular path. So in the vertical direction then, we've got the sum of the forces is 0. Okay, because in this vertical direction, the normal force is just being balanced out by the weight force. So F normal minus mg is 0, or, and this we've seen before in some examples, the normal force is equal to the weight. But in the x direction, here I'm going to call x, and this is something that I always want you to do in these problems, is define the x direction positive inward toward the center of spin. This is something we always do, because that's the direction of the centripetal force. And so it's got to be positive in the direction that makes the car go in a circle. So in other words, I could have set up the problem with the car over on this side when it's coming out at us. But in that case, my x direction would still be pointed toward the center. And so this is what I've got over here. The x direction is plus toward the center. And that's the direction then of the static friction force. Because if the car gets going too fast, it's going to start to slide away from the track. Okay? And so the centripetal force then of the static friction, as this thing goes around, plays the role of the tension in the string when we had a mass on a string. It's always pointed toward the center, and that's what deviates the car from its straight line, constant speed path. So this is our sum of the y equations. The Fy is 0, and that gives us the normal force equals mg. But the sum of the x forces is kind of the critical one here. That's equal to our centripetal force. which is our mass, times our centripetal acceleration. Remember, AC is equal to v squared over r, and so F is mass times centripetal acceleration, or mv squared over r. Now, we want the maximum velocity, and so what that means is the static friction force will only push as hard as it needs to. But if we want the maximum velocity, then that means that we are looking at pushing the static friction force to the breaking point. Okay, and so Fs max is equal to the coefficient of static friction times the normal force, which we know in this case is Vs mg. So the sum of the forces in the x, there's only one, that's Fs max, or mu s mg, that's equal to mv squared over r. So this gives us a condition now on the maximum velocity. So this is only true if we're talking about V max here. If V is less than V max, then the static friction force is not pushed to the breaking point. And if V is greater than V max, then it starts to slide. Okay? And so we're right at that critical point where it's just getting ready to slide. So that if we cancel out the m's, and that's why we didn't need m in this equation, is that the m's cancel. And so this means that as long as we know what the coefficient of static friction is, let's say in this case, mu s is equal to 0.5. I've been using that number a lot, but you've seen it can take on a variety of different values. But for this problem, let's assume that it is 0.5. Then we can see that V max from this fairly simple equation is the square root of mu s r g. Okay, when I just cross multiply by r and then take the square root, that gives me V max. Now in these kinds of problems, oftentimes you'll get a velocity that's related to the square root of rg with some other factor thrown in. And in this case, it's mu s times rg. So let's plug in the numbers and see what we get for V max in. That's going to be root of 0.5 times r for this problem. We set that equal to 200 times g, 200 meters, times g, which is 10 meters per second squared. So that's 100 times 10, or the square root of 1,000. We'll have here in a second. Okay, so that's 31.6 meters per second. So that's the fastest speed that the car can go before the car starts to slide off the track. Okay, and so that then would be for a flat race car track. Let's try another example now. You can look up at the data projector. And in this next example, let's say that we have a mass which is spinning around in a circular path of radius r, and we want to maintain the position of m2. Okay, and so that means that we've got to spin m1 around in a circle that has a, let's say that that radius r for this problem is equal to 2 meters. Okay, so we maintain that radius of 2 meters. Here's m1. And then here's m2 hanging. And we'll assume there's no friction at this point of contact, the hole in the table. Okay, so as M1 goes round and round in a circle, there's going to be a tension force. So now it's the tension in the string that is keeping M1 going around in a circle. Let's say here that M1 is equal to 1 kilogram and M2 is equal to 2 kilograms, the hanging mass. And we want to, in this problem, find the velocity that will support M2 without it moving. Okay, so we actually need two free body diagrams here. But for M2, this is a static equilibrium problem. Because by supporting here, we mean that it will not move. Which then tells us that the sum of the forces on M2 must be equal to 0. So we have a simple equation then for M2. We can just say that T minus M2G is 0, where T equals M2G. Now that's an important equation because the tension in the string here is also the same as the tension in the string that is supplying the centripetal force that is making M1 go around in a circle. So for M1, we have a second equation, and let's assume there's no friction on the surface. So M1 equation then is going to be the sum of the inward forces. So here again, we've got our x-axis and our y-axis. We're not too concerned about the y-axis here because there's no friction in the problem. And so we can just say then that the tension force is our centripetal force equals M1 V squared over R. Okay. And so that's just the sum of the x forces, and there's only one in this case, is M1 times A, that A is V squared over R. So we can solve this then for V. But before we do that, let's also note here that T is equal to M2G from equation 1. Okay? And so I can take that value for the tension and plug it in there. That gives me M2G equals M1 V squared over R. Or V squared equals M2 over M1 RG, where V is the square root of some numerical constant here. In this case, it's the ratio of the masses. In the last example, remember, it was the coefficient of static friction. So we're seeing kind of a similarity in the basic form that these equations take on when we are figuring out the velocity that is associated with a certain radius of our uniform circular motion path. So now we're ready to plug in some numbers. And remember, R was 2 meters, and so we can write this as the square root of 2 kilograms over 1 kilogram times R, which is 2 meters, times G, which is 10 meters per second squared. And that gives us the velocity that's equal to root 40. Which is 6.32 meters per second. All right, so that's the basic setup for this problem. So there are different variations on this, but it's the same basic kind of idea where you choose the positive direction to be toward the center of spin, Then you set the sum of those forces. In this case, we've only had one force in these examples so far. And set that equal to mv squared over r. In the next example, let's say you're on a amusement park Ferris wheel. And the Ferris wheel is moving with a constant velocity as it goes round and round in a circle. So when you're up at the top, you feel a slightly different sensation than when you're down at the bottom. Down at the bottom, you're going to feel a little bit heavier as you're sitting in here because of the fact that it is going to take more force to push up to keep you going in a circular path. So at the bottom, you'd have a normal force, you'd have mg, but the normal force would have to be bigger than mg because the difference between them as you're going round and round in a circle has to be equal to mv squared over r. Okay, so let's say that the velocity is constant. Here it's v, here it's v. So in this case, we'll be given v. We'll change it up a little in this one. Instead of solving for v, we'll be given v. Let's say that v for the Ferris wheel is 5 meters per second. So that's pretty fun then, about 10 miles an hour. You know, it's movement. That with a big radius too. So let's find then the apparent weight of a person who weighs 1,000 newtons on the ground. So in other words, this is the true weight, or that's equal to mg. Okay, so the true weight, mg, is 1,000. So from that then we can get m is equal to 1,000 newtons divided by 10 meters per second squared. This is something we always want to do if we're given the weight of a mass. And we're using F equals ma, is we have to convert that into a mass first before we do anything else. So just drop everything you're doing, convert it into a mass, and then you can move on. Okay, so the mass then is going to be 1,000 divided by 10, or 100 kilograms. So now that's good. We've got that the person has a mass of 100 kilograms and a true weight of 1,000 newtons. And so let's find the apparent weight of the person at the bottom and at the top. So in part A, at the bottom, our first objective then is to draw a complete force diagram. And I can tell you just from experience, I know that the normal force pushing up on the person has to equal the person's apparent weight. Okay, how do I know that? Well, because in order to push down, let's say there were a scale here that the person were sitting or standing on, that scale would be compressed. Okay, and so then the scale would push back with what's equal to the normal force. So we've talked about that before with the Einstein elevator problem, that the apparent weight is the same thing as the normal force in those kinds of problems. And that normal force has to be bigger than mg because the sum of the forces acting inward toward the center of spin, in this case is going to be F normal minus mg. That'll have to equal mv squared over r, because the sum of the forces toward the center of spin is equal to the centripetal force. That's what's making it go in a circle. Okay, and so this is our positive direction then. In this case, it would be like a positive y direction. And there are really no x forces to consider here in trying to solve this problem. Okay, so our normal force is the same thing as the apparent weight, and that's going to be mv squared over r plus mg. Okay, so m then, that's where we needed the m, was for F equals ma. Okay, and so the m then is 100 kilograms times the velocity squared, that's 5 meters per second, quantity squared, divided by, and now here we can set the radius of the Ferris wheel at 10 meters. Okay, and so that would be about 30 feet, so it's a pretty big Ferris wheel. Right, so we'll divide that then by 10 meters. And then we'll add to that mg, but mg is just the true weight, which is 1,000 newtons. Or we could take m, which is 100, and multiply by g, which is 10. That's what we did to get the m in the first place. So there's no need to go back and forth with that, as long as we understand that this is the true weight. Okay, and so here then, this is going to be 100 times 25 divided by 10 plus 1,000. And so that'll be 10 times 25 is 250 plus 1,000. So that'll give us our apparent weight of 1,250. So it's been upped by about 25%, because it was 1,000 and now it's 1,250. So it's an increase. So that's what you feel then when you're being crushed down into the, if you can just, let's just take a look here at this picture. You're being crushed down by the crunching action of having your direction changed, okay? So there's a centripetal force acting this way, but then the reaction force is you being crunched down. And so some people call that a centrifugal force, but that's really not really quite right to say that, although you are feeling a force that's kind of crunching you down from this accelerated reference frame. This is really just a natural result of changing the straight line constant speed path. So by pushing up like this, you will feel a reaction force which will tend to crunch you, but because it's in an accelerated reference frame, that's not considered to be a real force. We only look from reference frames that aren't being accelerated onto ones that are when we analyze the force diagram. And so although a centrifugal effect is often referred to, it is not quite right to draw a centrifugal force vector crushing this person down into the seat, but rather to say, well, the natural motion of the person is to go in a straight line. It's being deviated from that by this centripetal force, and then the reaction force tends to crush them down into the seat. Now in part B, we want to go to the top. Okay, so at the top of the path, we need another force diagram, mg, and the normal force. Now in this case, I'm making the normal force smaller than mg, because I know when you tend to go up over the top, you tend to feel lighter. As a matter of fact, you could feel so light that you would lift off. I actually know of a friend of mine who, at Disneyland on the Matterhorn ride, once stood up. He broke out of the harness that was holding him in, and he was standing up as this thing went over the top, and he flew out of the bobsled, and my friend had very fast reflexes, caught him by his ankles and pulled him back in. Okay, so that's an example of where the normal force went negative. Okay, but here, it's just, we're not going fast enough so that the person flies out, but rather they're just going to feel a little bit lighter as they go up over the top. And so this is a sensation you probably felt before when you've gone up over a hill and you felt a little lighter up at the top. Okay, so at the top then, we can say that the positive direction is still toward the center of spin. So that means mg is going to be in the positive direction. It's going to be mg minus f normal equals mv squared over r. So that's the sum of the forces at the top, giving us the normal force is equal to mg minus mv squared over r. So that's going to be 1,000 newtons minus, so it's basically this equation, but with a minus instead of a plus after the mg. Right, so this will be 100 kilograms times 5 meters per second squared, same numbers, divided by 10 meters, or that'll be 1,000 minus 250, so that'll be 750 newtons. So that's a decrease of about 25% in the apparent weight at the top, whereas at the bottom, we had an increase of about 25% in the apparent weight due to the acceleration. So that's the way to handle a problem like that.